So these formulas show us how to take the parameterization of the surface and take the parameterization of the surface and calculate things here. Let me make it a little bit bigger. So we introduce, I'm sorry, Hefe, LJEF. E, F, and G. There is an E, F, and G there. My camera may not be showing it as it is the evil green, which my camera does not pick up. But there is indeed an E, F, and G. E is the dot product of the partial u velocity with itself. The partial velocity u, like partial x, partial u, partial x, partial v dotted with each other, that's the F. The G is the dot product of the v partial derivative with itself. All right. And so like the dot product of two vectors is given by this particular linear combination of the components with respect to, you know, the Cartesian coordinate system and these coefficients, E, F, and G. Lagrange's identity, if we can introduce the magnitude of the cross product, right? So straight up here is a formula for the unit normal. Here's a formula for the unit normal in terms of the warping functions. You see? So xu cross xv normalized. This is the definition of the unit normal. We learned it in Calc 3, right? Well, the length of this is given by that because of Lagrange's identity. It says that that length is equal to this, but that's the square root of this. So there's a formula for the normalization of the unit vector in terms of the warping functions E, F, and G. Great. Then what? Well, we then introduce second partial derivative, like, you know, xuu, xuv, xvv. And we use those to define these things. I don't have names for these. I do refer to this general corner of differential geometry as alphabet soup because it's very soupy and very alphabety. But L, M, and N are dot products of the shape operator with the partial velocities. All right, like that. And turns out you can prove that the formula for the Gaussian curvature is simply that, and the formula for the mean curvature is simply that. All of those things are simply calculated from, well, the L, M, and N don't seem that simple, right? It seems like we still have to calculate the shape operator at this point, doesn't it? We will soon get rid of the shape operator, though. We'll just have formulas in terms of partial derivatives. So this and that are just nothing more than the identities I wrote over there put together with what we're doing. There's not much to say about this here. So then what? Well, then we've got this wonderful lemma that you can write the L, M, and N instead of the shape operator. Ooh, look at that. We just traded the shape operator for the unit normal dot the second derivatives of the parameterization. The shape operator has now left the building. See the calculus? Yeah. The calculus here now just depends on second partials, the unit normal, right? And so, hooray, now we can calculate L, M, N, E, F, G without ever touching the shape operator, and we can calculate the Gaussian curvature and the mean curvature. So I do it. This is called a helicoid. It is a spiral ramp. It's like a helix, but it kind of like I got some Let me show you. Well, that's not a helicoid. That's a catenoid right there. As you can see, catenoid. And what's he going to do? Oh, look at that. Look at that. Let's see what's happening. Whoa, dude. That's a helicoid. He's got a sign for it in just a second here. Show us. Come on. Come on. Do it. Do it. Do it. Do it. Come on. As you can see, helicoid. That proves it. So, let's not do that. There we go. There's no telling what YouTube ads are going to show you. Let's see here. Anyway, so here's the calculation of the warping functions and the LMN for the helicoid. So it's straightforward. This is very relaxing. given some of the other things we've done this semester, these calculations are very relaxing, right? But there they are. And there's the cross product. There's the unit normal. Here's your L. Here's your M. Here's your N. Put it all together, we've got what? Gaussian curvature and mean curvature. So the Gaussian curvature, after you work out your alphabet soup here, here's your Gaussian curvature like so. Your mean curvature 0. So apparently, the helicoid is a minimal surface, although it's not flat, as was pretty obvious from the picture, right? Although a cylinder looks flat. Does a cylinder look flat to you? I don't know. That word, yeah, that word, flat. Remember this. The Gaussian curvature is minus b over b squared plus u squared. Okay, remember that. You can work out the principal curvatures. They're those. Great. Here is the alphabet soup for the cylinder. So you got your warping functions, r squared 0, 1, your LMN, calculate your unit normal, Gaussian curvature 0, mean curvature minus 1 over 2r. Simple as that. These are the things that Gauss worked out. This is all Gauss's stuff, I believe. I think this notation may even be due to Gauss. It's very old. This is the saddle surface. And I do in the previous lecture have the shape operator worked out from specifically looking at curves and sorting through the name of that thing. The covariant derivative definition in terms of curve stuff. Like I actually have that calculation. But here is an easier one. There's your parameterization of the saddle surface. There's your warping functions, your LMN. So that's the Gaussian curvature. Minus 1 over 1 plus u squared plus v squared. You see I was lying when I said k was minus 1. I was lying. Well, it was a lie of omission. What I omitted was it's minus 1 at the point where u and v are both 0, namely the origin. Everywhere else, that's its curvature. And the mean curvature is 0 at the origin, but it's not 0 everywhere. So I have to retract one of my statements. The saddle surface is not minimal. It'd have to be 0 everywhere to be minimal. It ain't the case. All right. This is a homework problem, which is cool. Here's another homework problem, which is cool from the book. We don't care. Implicit case. Oh, man. Son of a gun.
Are you familiar with mean curvature flows?
Mean curvature flows? Nope. I don't know too much about all that. This one's interesting. There's the Gaussian curvature for the ellipsoid. So the last couple pages are formulas for the Gaussian curvature for a function that's defined like as a level surface. I wrote that formula down from a book I have, but I don't understand how to derive it. I'd like to understand how to derive this. I don't know yet at the moment. It's just like a super cool formula. Like if you know, if your surface, think about this, if your surface is f of x, y, z equals to a constant, you want to calculate the Gaussian curvature, all you have to do is calculate these partial derivatives, shove it in a matrix, calculate the determinant. That's the Gaussian curvature. That's a really slick formula.
Was that in the linear algebra?
I don't think so.
Huh?
I don't think so. So, yeah. So the larger point here is that if you study these things that we're looking at, so this, come on, I said play. So this one's, I like this one in particular because, let me try to explain what's going on here. I was hoping I had the other thing in this notes. I see I don't. But if you worked out the Gaussian curvature, I believe it's the Gaussian curvature, and maybe so the Gaussian curvature of the catenoid and the Gaussian curvature of the helicoid, they're equal. Which means actually that these surfaces are locally isometric, which means that you can bend one into the other in this fashion. They're both also minimal, I believe. So they're both.
Why he did that.
Mm-hmm. So there's in fact like a whole family of surfaces between the catenoid and the helicoid, and you can do like a smooth deformation from one to the other, smoothly toggling between these. The formulas are in Wikipedia. So as you can see, that's the catenoid, helicoid, catenoid, helicoid, catenoid, and these give you, I'm thinking here, the deformation parameter theta. When you get to pi, it's a right-handed helicoid. When you're at plus or minus pi over 2, it's a catenoid. And when you're at 0, it's a left-handed helicoid. Ooh, yeah, because you can either have the helix go like this, or you can have it go like that. So I don't know. This is, to me, this is the coolest example in all of elementary differential geometry to really understand how it gels together with the things we're looking at. It's very interesting. So where we're going. Now we have a definition of the Gaussian curvature and the mean curvature. These are based on the unit normal, right? Which has to do with where the surface is in 3 dimensions, right? And it turns out that part of this has to do with how we've put the surface in 3 dimensions, but part of it is like intrinsic to the geometry of the surface itself. It turns out that the Gaussian curvature is part of the intrinsic geometry of the surface, whereas the mean curvature has more to do with just kind of how we've embedded the surface in R3. And so we're going to discover how that all works out and discover what's called Gauss's awesome theorem. Gauss's awesome theorem is basically the discovery that the Gaussian curvature is independent of things outside the surface. And we'll see how to write that in terms of differential forms. It's not apparent yet. These are the classical formulas of Gauss, and we have to have these as a background, if nothing else. So I think I did actually ask you guys to calculate a couple of these things, but it should be pretty easy with these formulas, which if you have trouble finding them, let me know.